What's in the recipe? What do you need to cook up a quark? Well, this particular model says you need three main ingredients. First, you start with a generic quark, which is kind of like a basic template. Then, you need these particles called scalar bosons. You can think of them as the energy-packed glue that holds things together. And finally, you have the truly fundamental bits, which this model calls rishons. These are the ultimate ingredients.
And this is where it gets really cool. Because, a good theory can't just list the ingredients. It has to show you how they combine to make something real. And just as important, it has to show you how they break apart. So let's see how this model actually puts its recipe to work.
We're going to start with a real celebrity in the particle world, the top quark. This thing is a beast. It's the most massive elementary particle we've ever found. Now, according to the standard model, it's fundamental. But in our Prion model, nope, it's built out of smaller pieces.
Okay, I know this diagram looks a little intense, but let's just break it down together. Just focus on that very top row. That represents our top quark. According to this model, it's a combination of two bigger chunks, a generic D quark on the left and something called a boson plus in the middle. But look closer. You see those little pie chart things inside? Those are the rishons, the really fundamental particles. And it's their specific arrangement that gives the top quark all of its unique properties.
But see, building the particle is only half the battle. The real test of a model like this is whether it can also explain how particles behave in the real world. And the top quark is famous for being incredibly unstable. It decays almost instantly. So let's see if this model can actually predict how that happens.
And here we go. This shows the whole process. That top quark in the first row is unstable, right? It falls apart, and it decays into a bottom quark, which you see there in row 2. Now look at how the little rishons inside have rearranged themselves. That reshuffling releases a burst of energy which forms a whole new particle that could shot out. That's the W+ boson in row 3. So the model isn't just saying this happens, it's showing a plausible how. It's a mechanism for the building blocks to reshuffle. So, okay, we've got a recipe that can build quarks and can break them down. That's a really good start. But to be taken seriously in physics, any new theory has to do way more than that. It has to perfectly match all the known, tested, confirmed results of the standard model. It's got to pass the quantum test. And this is the absolute make or break question, isn't it? Do the properties of these composite, home-built quarks, their electric charge, their spin, all their quantum numbers, do they actually match what we measure in our giant particle colliders? Because if those numbers don't add up perfectly, the theory is, well, dead in the water.
All right, let's check the numbers, starting with something really basic, electric charge. And would you look at that? The model predicts the top quark's charge is positive 2/3. Perfect. For the bottom quark, it predicts negative 1/3. Another match. For the charm quark, positive 2/3. Yes again. In every single case, it's a perfect match with what we already know is true. That is a huge first step.
Okay, here's another critical test. It's a quantum property called isospin, which has to do with how particles interact through the weak force. The standard model absolutely requires these heavy quarks to have a total isospin of 0. And what's so amazing is that in this model, the individual prions inside do have isospin, but they are arranged in such a way that their values cancel each other out perfectly. That's not a lucky guess. That is just elegant design.
And the checklist just keeps going. The model correctly handles color charge, which is the force that glues quarks together. It calculates the correct spin for each quark. That's its natural built-in rotation. And it even has a neat way to explain flavor. What makes a top quark different from a bottom quark, by assigning that property directly to the rishons themselves. It's a really comprehensive attempt to get all the tiny quantum details right.
So let's pull back and zoom out for a second. What does this all really mean? We've just taken this incredible journey deep inside the quark, exploring a theoretical blueprint for a hidden layer of reality. This is what physics on the absolute frontier looks like. It's messy, it's theoretical, and it's exciting.
I think this quote from the source material just nails it. This model we've looked at probably isn't the final answer, but it's a perfect example of the scientific process in action. It's a detailed, mathematical, and incredibly logical attempt to ask what if, and then to really, rigorously follow that question all the way to its conclusion.
So what are the big things to take away from all of this?
First, the idea of a deeper layer to reality isn't just science fiction, it's a serious scientific pursuit. Second, physicists explore these ideas using theoretical new ingredients, like prions. But third, and this is the most important one, is the quantum test.
No matter how cool an idea is, it has to match all the properties of particles we've already measured. And finally, all of this shows that the quest continues. The search for the ultimate particle is far from over.
Hello and welcome back to The Explainer. Today we're diving into one of the biggest questions in all of physics. Why do the fundamental particles of our universe weigh what they do? We're going to explore a really fascinating and kind of radical theoretical model that suggests an answer. It frames mass not as some fundamental ingredient, but as the result of a cosmic recipe. So we know our universe is built from things like quarks and electrons, but the real head-scratcher is why one of these particles weighs next to nothing, while another is hundreds of thousands of times heavier. Our best theory, the Standard Model, is incredible at telling us what these masses are, but it sort of just shrugs when we ask why they are what they are. It's like having a perfect list of ingredients with their weights down to the microgram, but absolutely no recipe telling you how they all connect. I mean, just look at the sheer scale of this thing. On one hand, you've got the top quark, the absolute heavyweight champion of the particle world, clocking in at around 400,000 times the mass of an electron. And for this explainer, we're going to use the electron's mass as our basic unit of measurement, our EU. But then, on the other hand, you have the d quark, which is a total featherweight at just 10 EU. The thing is, these numbers aren't random. They're incredibly precise. So what gives? How does the universe follow a set of rules to produce results that are so specific, yet so wildly different? All right, so the framework we're digging into today offers a pretty wild idea. It says mass isn't a fundamental property a particle just has. Instead, it's compositional. It's something that's built. This theory basically treats mass like a cosmic recipe, where a particle's final weight is just the result of mixing simpler things together according to a very specific set of instructions. Okay, so what's in this recipe? Well, according to this model, everything starts with a base ingredient, a generic particle. Now, this isn't something we can see directly. Think of it more like the plain flour or sugar for our recipe, a theoretical starting point with a set mass. For example, the model says there's a generic d quark that starts things off with a mass of 200 electron units. Our model actually goes one level deeper. It suggests that even these generic particles are made of something smaller, components called rechons, and the initial mass depends entirely on how these rechons are arranged inside. There's a simple but powerful rule. If a certain kind of rechon is by itself, singularly expressed, it contributes a mass factor of 10. But if it's paired up with another one, that factor drops all the way down to just 1. Okay, let's walk through an example so you can see how this works. Let's calculate the mass of a generic down quark. First, the model starts with a base value of 20 electron units. Think of EU as just a convenient way to measure. Now, the generic d quark has one of those lone wolf, singularly expressed rechons inside it. And what's the rule for a single rechon? It gives us a mass factor of 10. So we take our base value of 20 and we multiply it by 10. And boom, just like that, you get the initial mass for the generic d quark 200 electron units. What's so cool about this is that it's not a number just pulled out of a hat. It's the direct result of a simple rule about the particle's internal structure. And the exact same logic applies to the other generic particle, the up quark. In its case, it has 2 of those single rechons, so its calculation is 20 times 10 times another 10. That gives it a much larger initial mass of 2,000 electron units. So right away, even at this basic level, the model gives us a clear reason for why one is heavier than the other. Of course, no recipe is complete without spices. And in this schema, the spices are scalar bosons. These are theoretical particles that interact with our generic ones. But they don't just add a little flavor. No, they apply a mass factor. They can multiply or divide the base mass, kind of like a super potent spice that completely transforms the entire dish. So you might be wondering, how does the recipe know whether to multiply or to divide? Well, that's where the cooking instructions come in. The model calls this the combinatorial value, or CV for short. Each ingredient has one, and the rule is dead simple. If you multiply their values together and the result is positive, the mass goes up. If it's negative, the mass goes down. That's it. That's the core mechanic that runs the whole show. So, let's just put it all together. This whole cosmic recipe really just boils down to 4 simple steps. First, you pick your generic particle. Second, you add a scalar boson. Third, you check the combinatorial values to see if you're going up or down. And fourth, you apply that mass factor. A surprisingly simple process for building the entire universe, right? All right, enough theory. Let's get our hands dirty and see how this recipe actually works. And we're going to start with the biggest challenge on the menu, the top quark. It's the most massive fundamental particle we've ever found. So, can these simple rules really cook up such a heavyweight? Let's find out. So, how do you make a top quark? Well, according to this recipe, you start with our generic D quark at 200 EU. But then something really interesting happens. The model says a specific scalar boson performs what it calls an electromagnetic conversion, which transforms that D quark into a much heavier generic U quark with a new mass of 2000 EU. And then that same boson applies its mass factor, a whopping multiplication of 200. And the math from there is almost beautifully simple. You just take that new 2000 U mass of the generic U quark, you multiply it by that 200 factor, and you get 400,000 electron units, which is remarkably the measured mass of the top quark. So here's the crazy part. According to this model, the recipe for a D quark is really surprising. You'd think it starts with a generic D quark, wouldn't you? Nope. It actually starts with the much heavier generic U quark. Then it gets transformed. This diagram here kind of shows the whole process. I know it looks a little complicated, but just focus on that top row for a second. See on the left? That's our starting ingredient, the generic U quark. And then it interacts with something called a boson minus to create our final particle. Okay, let's actually walk through the math. It's pretty straightforward. Step 1. We start with that generic U quark at 2000 electron units. Now, that boson minus does two things at once. First, it converts the U quark into a generic D quark. So our new base mass is 200 U. But at the same time, that boson minus applies its mass factor, which is a decrease by a factor of 20. So we take our new mass of 200 and we divide it by 20. And what do you get? 10 electron units. That's the final mass of the D quark. Okay, so the recipe seems to work for quarks, but that's just one family of particles. To really put this idea to the test, what about a totally different group, the leptons? Let's see if this same recipe can build one of the most famous particles of all, the electron. Now, this is pretty cool. For the electron's recipe, the model says the generic form is actually another particle we know, the muon, which has a mass of about 200 mu. And for this particular recipe, the combinatorial value turns out to be negative. So just like before, instead of multiplying, the rules tell the boson to take that base mass and divide it by 200. And look what happens. You take the muon's mass, 200 U, you divide by the factor of 200, and you land squarely on 1 U. I mean, think about that for a second. The model uses the electron's mass as its fundamental unit of measurement, and then it turns around and derives that very unit from a heavier particle just by following its own rules. It's incredibly tidy. Now, this is where the model goes from being an interesting idea to something that makes you go, wait, what? Because as the creators of this model applied the recipe across the entire lepton family, the electron, the muon, the tau, and all their neutrino partners, they apparently stumbled onto a pattern, a stunningly consistent hidden number that seems to connect all of them. That number is 160,000. And the model claims this isn't just a coincidence, it's a consistent mass scaling factor. The claim is if you take the mass of a charged lepton from any generation, like the electron or the tau, and you divide it by 160,000, you will get the precise mass of its neutrino partner. So let's take the tau lepton as an example. This model calculates its mass at about 4,000 electron units, and it calculates its partner, the tau neutrino, at a crazy tiny 0.025 EU. Now do the math yourself. What's 4,000 divided by that magic number, 160,000? It's exactly 0.025. According to the authors, this relationship holds true for the other generations too. It just clicks. So the big question is, where in the world does a number like 160,000 even come from? Well, this is where the authors make a really striking connection. They state that this value in electron units is comparable to the mass of the W boson. And the W boson isn't just any old particle. It's the particle that carries the weak nuclear force. The implication here is huge. Their scaling factor might actually be directly linked to one of the fundamental forces of nature. So what do we do with all this? Let's just zoom out. If a model like this turned out to be right, it would mean that the whole complicated zoo of particle masses isn't arbitrary at all. It would mean it's all the result of a deep, underlying logic, almost like a cosmic grammar that's baked right into the fabric of reality itself. So let's quickly recap the core claims of this model we've just walked through. First, the big one. Mass isn't fundamental, it's built from other parts. Second, a few very simple rules can produce the huge, complex range of masses we see. Third, this consistent scaling factor of about 160,000 seems to pop up, connecting charged leptons to their neutrinos. And finally, and this is key, the authors claim their results are totally consistent with the measured values we already have from the standard model. And that really just leaves us with a final, fascinating thought to chew on. This model treats mass not as a given fact of the universe, but as the result of a calculation. It reframes a constant of nature as something that emerges from a deeper, simpler system. So it really makes you wonder, if the mass of everything is just the outcome of a cosmic recipe, what other parts of our reality are just waiting for us to figure out their instructions?